Okay, sorry. Good afternoon, everyone. So here presenting Professor Paul Barddal, that has this very French name, but it's from Brazil and doesn't speak French, unfortunately. So he's a professor from the PUC Paraná, and it's going to be here talking about data stream mining, going beyond training and testing. So I believe a lot of you work a bit with like this idea of incremental learning. So hopefully we're going to get some interesting points from it. Okay.
Thank you. Thank you for the introduction. So as Rafael said, my name is Jean-Paul, which is a very popular French name, but I don't speak any French at all. And also I do not come from a French family, so it's just the name, and I apologize for that. So I'm going to be talking here today about data stream mining. I'm not sure if any of you are acquainted with this topic. Okay, just two folks, okay. So I suppose most of what I'm going to talk to you about is going to be new, which I think it's a good thing, right? So let me just move here. I'm a professor with the graduate program in informatics. I live in the south part of Brazil in a place called Curitiba. And I do research mostly on data stream mining. So when you think about data stream mining, we have the same tasks that we have in traditional machine learning. So you can think about classification, regression, clustering, feature selection, whatever. It's all in there as well. I do have some applied ML projects with companies, with the industry. They do not necessarily reflect research on data streams, but I do that as well. And I'm going to leave you my email, my website. So if you want to reach out and discuss any of the topics I'm going to talk about, just feel free to do it. All right. Okay. So moving on, let's talk about data streams first. I think it's important that we are familiar with what I'm talking about here today. So when we think about data streams, we are talking about potentially unbounded or infinite sequences of data. And here I'm going to use a notation which is related to classification. So we have a feature vector, which is referred to here as X, and classes Y. But the problem is that we do not necessarily have a data set that is available to us. This means that the data is ever flowing, so we get one instance at a time. So we need to do our best in the sense of not only processing such data, but also mining this data. So if we're thinking about classification, regression, clustering, we need to be able to somehow update our models accordingly to how data becomes available. There's also some research in the sense that we do have an inherent time component here, right? And some researchers also discuss on whether data streams are time series. So I'm going to leave you a reference for later so that you can read it and maybe draw your own intuition about it, okay? So what are the first requirements that came up when thinking about data streams? So the first one is, well, since we have instances arriving one by one over time, I mean, we need to process each instance individually. So this is what we call single pass processing. Okay. The second requirement regards memory consumption. So if you think about, yeah, sure.
Sorry, so you cannot have a mini batch?
Yes, you can. And this is actually referred here in the second requirement. So you can maybe have a mini batch. You can, for instance, buffer some instances, but the problem is that you should be able to bound this, limit this, okay? And this is why, I mean, you should not have like a potentially infinite buffer, because otherwise the system will crash. Okay, so you can have a buffer, but usually you try to think about how you process each instance individually. Okay. The next up, we have processing time. So similar to memory, you can also think about time restraints. So for instance, if you have a buffer, I mean, if your buffer increases and you have to process that buffer, I mean, over time, processing will grow as well. So these things are actually very related to one another. And number 4, I mean, we have to be able to predict at any time. So this is, again, also connected to the previous ones, but the idea here is that once you have a query to your classifier or regressor or whatever, you should not have a huge delay on providing a result for that instance. Okay, so far so good? Sweet. So there's this process which is called frequential, and I think this is one of the most intriguing parts of data stream mining, because this is where we go beyond training and testing. I mean, we're going to continue to have these both steps, but they're actually going to be interleaved. So since we have a stream of data, what we're going to do is, well, we are going to first query such an instance. I mean, we're going to do a prediction, and then we're going in a training step. All right. And this is nice because if you do that, you're able to compute how good or bad the performance of your classifier is. So there's this frequential error, which is basically computed along windows. And this is very easy for you to do, but most of the tools we have today, they already compute this kind of stuff. But what I want to give you is like the general idea of how we usually work in streaming settings. So this is just a pseudocode. We have a stream as input and a classifier. So assuming that we have a stream, it's potentially infinite. What we do is, well, we gather the next instance, right? We query your classifier for that. I mean, you get a prediction. You analyze, so you determine if it's correct or not. And then later what you do is, well, you update your model with the correct label. Okay. So this is what we call frequential. And again, I know this is very different from traditional batch learning, right? Because in batch learning, you do maybe holdout or k-fold cross-val. But again, we are thinking about data that is arriving over time. Okay, sure.
Does it mean that you evaluate while also using the same data for training?
Yeah.
Right?
But the key point here is actually my last comment here. You always train before. Actually, I apologize. Yeah, you always test before training. That's, I mean, an imposition. There's no way you can like do the opposite, right? Okay, so back to frequential here. Yeah, sure.
So I was wondering, so let's assume that the speed of the arrival is like faster than the speed of training. Do we have any buffer to kind of like locate those, or we're gonna get rid of those inputs?
Yeah, in theory, yes, you would need to buffer your arriving data, but if you realize that training is not fast enough, it's gonna fail eventually. So that's problematic. You should avoid at all costs this kind of condition.
What are the scenarios for stream training though? I mean, because it seems risky, right?
Yeah, it is. Yeah.
So is there like you assume that there's a training phase where you have your system operating and you could train, or do you have you cut off and say, okay, I've done enough training, and then I'm in operating mode?
Yeah.
Because otherwise, if you have data with overlap, I don't see how you can train reliably.
Yes. Yeah, it really depends on the application, because let me give you like some examples. So for instance, assuming this exact very framework right here, we do have one big assumption is that, well, your instance arrives, you test it, right? And then before you receive the next instance, you already have the label for that instance so that you can update the model. So this is unrealistic, right? So in operation mode, what what is actually going to happen depends on the application itself. So there are scenarios in which you have a very large test phase. I mean, you have a lot of instances incoming, but at certain points, maybe you get a single instance, or maybe you're going to get a batch of data that you have now labels for, and then you can update it. So there is no strict or rigid approach on how you actually have those two steps, like the test step and the training step. What I'm trying to give you, as a message here today is that we try to develop algorithms that are able to update themselves on top of one single instance. If you are able to do that, it doesn't matter if you get one or thousands of instances. And how you actually interleave those steps is not going to matter as well. Make sense?
Yeah.
Sweet. Okay, so there are some challenges. I think I've actually talked about a couple of them right now. So for instance, the assumption that you get the label right after the arrival of the instance is too naive, maybe unrealistic. There's also this such scenarios in which you get batches of data every now and then. So again, it really depends, okay? So thinking about classifiers, I'm pretty sure you're gonna see lots of familiar stuff here. So for instance, KNN, I suppose all of you are acquainted with KNN, right? Very basic, very trivial, I can put it this way. So it's a lazy classifier, right? There's no actual training step. You just store the instances that you have. When we are in a streaming fashion, what we do is, well, we buffer some instances, right? And we usually use a first in, first out kind of storage. So more instances arrive, you put them in a buffer, and you just delete the older ones, right? But we do have one major issue here is that, well, how can we define an appropriate window size? I'm going to talk to you about concept drift later on, which is like key in data streams. But what I'm trying to say is that, well, if you are in a stable period, instances are coming from the same distribution. You can have a fair amount of instances. It's going to be okay. But if something comes up, your data distribution changes, it would be nice if you just kept maybe a smaller window, just the most recent data, because the past is going to be deceiving, right? It's going to be garbage. So there are some techniques for adaptive windowing, but it really depends. It's not trivial, and KNN is actually quite slow. So if you go back to the requirements I talked to you about earlier, not the best option. Second up, naive Bayes. So again, very similar. I suppose all of you are acquainted with this as well. And this is strictly what you are acquainted with. Since we're talking about probabilities, all you need to do is, well, increment contingency tables, or maybe the Gaussian estimates. Should be straightforward, right? The problem is, at the same time, KNN is able to forget the past because you do have this first in, first out approach. Naive Bayes doesn't do it. You're just incrementing data. And in the end, we have Hufting trees. Any of you ever heard of Hufting trees before? Yeah, okay. You're biased. All right. So I think this is one of the main algorithms we have for data streams. On top of that, we usually create ensembles, but I think it's important, if this is your first moment with data streams, for you to be familiar with this, okay? So Hufting trees are purely incremental trees, decision trees, and we usually start the process of learning a tree with a single leaf node, okay? So as new labeled data becomes available, what you do is, well, you wait until you account for n instances. This is here somewhere. here, the formula, oops. And this is what we call as, referred to as the grace period, okay? So at the moment you actually collect data about n instances, what you do is, well, you rank all of your features using some kind of heuristic measure. So information gain, Gini index, whatever, you can pick it, right? Next, what you do is, well, you compare the two best ranked features. I'm going to refer to them as xi and xj, and you compare that to the Houghton bound. So basically, this formula is going to tell you, well, do we have enough data? And is the difference between the two best ranked features enough for us to split, to branch the tree? And if so, what you do is, well, you replace the leaf node by a split node and you continue learning, right? So this is, again, a purely incremental approach, right? So in a nutshell, again, what you do is, well, you wait until you have data about n instances, you branch and you branch and you branch again, right? The good thing is that it has constant learning time, in the sense that once you get to a leaf node, the decision on whether to branch or not and how you branch it, there's no computational differences over time. Of course, as you have more and more data, the tree is going to grow a lot. And this is actually a problem. They can be ever growing. So if you go back to the constraints I talked to you about earlier, it's going to be problematic as well. But if you have a static data stream, there are no changes on that. The Houghton tree is actually going to converge to any other batch tree that you're familiar with. So it depends on the scenario. So far, so good. Any questions? Okay. Well, the biggest challenge we have in data streams is what we call concept drift. Some works also referred to as concept shift. It's going to be the same thing, right? It really depends on the area of machine learning that you're working with. What I'm trying to tell you is that, well, the word's dynamic, right? We're constantly producing more and more data, right? And I think there's like this rationale that the data that we produce maybe yesterday or months or years later is not going to have the same distribution that we'll have today, right? So if we train a model using older data, it's very unlikely that it's going to be generalizing well in recent data, right? So I like to give the pandemic as an example, right? We were used to many things before the pandemic, and I'm pretty sure we lost so many of these habits that we had, right? For instance, I'm not sure if you guys were used to maybe hybrid meetings like this. At least we were not. So this is like a result of the pandemic. And if you think about maybe consumption patterns, things like that, they also changed. So the key here is that the pandemic was totally unexpected, right? It was a major change, but perhaps there are other changes that we maybe do not realize, but they are actually taking place nonetheless, right? So what I'm trying to tell you is that maybe we have a data distribution like here on the left, right? Thinking again about classification. We can maybe have a real drift. So in the sense, the class boundary or the boundary between classes is actually changing, right? So the way you were used to label instances now is not the same anymore. And we also may have virtual drifts, which are not too problematic because the distribution is changing, but how you would label such instances does not. So again, real drift's more challenging than the others. And we can also think about how concept drift takes places over time. So there are some changes which are very abrupt. So from one instance to the other, the whole thing changes, right? There are some more smoother changes. So there's a time span that the change actually takes places. You can also think about recurring concepts. So things are one way, they change, and then perhaps they come back. This is often related to seasonality, perhaps. And there are some outliers, but I don't think they're too relevant here today. Well, motivated by concept drifts, a lot of research has been put on drift detectors. So I'm going to give you some references here today. If you're interested on them, you can check them later. But what people usually do is, well, they use this statistical drift detector to analyze the output of the classifier. So what we try to do is actually, we analyze the error rate of the classifier and we see if it's changing, right? So, I mean, the general idea would be like this. We do have instances, we are in that sequential loop, right? So we are testing and training. But now, after you test, you get a 0 or a 1, or for regression, it could be like the difference between the real and the prediction, right? And you use this information as input for the detector, and eventually it's going to tell you, well, we have a change. And if a change comes up, well, we're going to reset the classifier. So this is one of the first ideas that came up for concept drift adaptation, right? But I do have a question for you guys. It's like, what happens if we have a false alarm? We do not have a change, but the detector is telling us we do have one. What's going to happen? Yeah, I'm simply going to lose all of the knowledge that I gathered from previous data, and I shouldn't, right? And this is one of the main reasons on why ensemble-based approaches are so popular and why they are actually so good compared to what we saw before, right? Usually in ensemble-based classifiers, what we do is, well, we couple each member of the classifier with a drift detector. And since we have different data being coupled with each member of the pool, the drifts may be detected by different classifiers. Maybe some classifiers will not detect such changes. So if you have a false alarm, it's going to hurt just parts of your ensemble, not the entire system. So this way we are able to diminish the impact of false alarms. So in this sense, there's one key reference that I would like to bring here to you is what we call the adaptive random forest. As you can tell, it's totally related to the traditional random forest. This is something that we developed many years ago in the lab, even though we published that in 2017, so it's quite a bit of time already. It's still one of the major contenders in data string mining. So the idea is, well, we're going to learn trees in a Huffing tree approach. We're going to try to keep the main characteristics of the original random forest. So we analyze just parts of the feature space and so on. But we do have one thing in particular that I would like to draw your attention to, is what we call the background learning. So think about a random forest. Each tree has not only one detector, it actually has two detectors. So what we do is, well, we do have the traditional drift detector, and we're going to have another detector that we're going to refer as the warning detector. It's roughly the same thing, but what we do is, well, we change some of the hyperparameters of the detector, so it's going to be more sensitive to changes. So what we actually expect is that the warning is going to be flagged before the drift one. So when we do that, I mean, when we have a warning zone, what we do is, well, we actually start preemptively to learn another tree in background. So when the drift actually comes up, we do have a tree, an alternate tree already trained, and we swap it. So in this way, we are actually able to improve drift adaptation by large amounts. Okay, so if you are interested in this kind of stuff, I'm going to leave you two references, some tools for running experiments like this. The first one is the massive online analysis, which is not new. It's been around for quite some time. It's written in Java. It's well tested. You do have this graphical interface. It's very easy for you to set up and run experiments. And we have this under development tool called River, which is Python. It's very similar to scikit-learn. Should be straightforward if you're familiar with it. But again, this is under development. There's still some bugs here and there. If you're just starting with the topic, I would say go with MOA first. You're less likely to face issues. Okay. And what are the challenges we have these days? Okay, I'm going to give you like a small list here, but there's plenty more. So for instance, delayed labeling. So again, if we go back to that restriction on assuming that we have the label of an instance right before the next instance comes up, again, too naive. The real-world applications are not like that. We have semi-supervised learning as well. What happens if you just have the labels of some instances? I mean, there's a lot of data coming. You're not going to take any advantage of those, right? We do have a very strong relationship with continual learning because this is not actually the same thing, right? Because when you think about continual learning, what you're trying to do is, well, I do have a model for one specific task and I'm going to move it. I mean, fine tune it maybe to another task. But I think there are some concepts that could be brought together, that they could be combined. And again, deep learning, of course, online tuning. When we are about to run experiments like these, we do have lots of hyperparameters and classifiers. So how can we actually tweak those maybe during execution? This is a major research gap. Grain data stream mining, because again, it's not about just developing algorithms. You need to make sure they're not too energy. Energy consumption is not too high. And finally, the combination of maybe batch and stream learning, because again, if you have too many false alarms, it would be nice to have maybe a well-trained batch classifier in the end. And again, this is just to tell you, like, there are researchers that are focusing a lot of attention on the first two topics that I talked to you about regarding delayed labeling and semi-supervised learning. Okay, makes sense so far? Okay, so I'm going to spend maybe the last few minutes here talking about some of the ongoing research we have in the lab. I do have a student that will be arriving here in early November, so I think it's going to be important for you to be acquainted with the kind of stuff he's working on. So before that, just talking a bit about grain computing and data stream mining. So I mean, when we run experiments, for instance, using the MOA tool or River, we get not only accuracy and precision recall, traditional ML metrics, but we also get the processing time and also memory consumption rates. But there are some researchers that have actually found out that there's no clear relationship between processing time, memory consumption, and also energy consumption. Because there are so many things involved. It really depends on the architecture of your computer, if you have multi-threading or not, and so on and so on. So what we did is, well, we tried to assess how much energy an experiment was actually consuming using REPL. I'm not sure if you're familiar with REPL. It's a tool available in Linux. And we actually have this information now inside MOA. I know the image is not so clear, but when you run an experiment in MOA, you're going to see a screen like this. And we added a couple of columns there to show actually how much energy an experiment is using. We do have some limitations, some gaps for the moment. So this is Linux only. And again, this is limited to REPL, right? It works pretty well with Intel CPUs, but AMD, I mean, it's not really the same thing. I mean, there are some limitations in REPL and no macOS support as well. So we're still thinking about the best way to actually have something that is common ground for all operating systems and architectures. But what I would like to draw your attention to is textual data streams. So think about Twitter, for instance, right? Or X. I'm not sure how people are calling it these days, but I think that's one of the main streaming settings we have, which a lot of people use, I mean, on a daily basis. And think about what actually goes on in a social network like that. I mean, maybe the words, when you think about the word and their meaning, they're changing over time, right? Can you guys give me an example of that? Nope, I'm gonna give you a couple. You can also think about the relationship between words, entities, things like that. Maybe your sentiment towards a company or an institution is going to change for whatever reason. Maybe there's some new words, some new languages that are being used. So if you have a machine learning model that wants to learn anything from textual data, it's not trivial, right? Or maybe you have an event. Maybe some politician tweeted something bad on the internet. Everything goes crazy. So it happens a lot in Brazil. So let me give you a couple of examples. This is not related to data streams, because here you're going to see some words and how they actually evolved over decades. So this is something I wasn't actually very acquainted with, but taking the last example, the word awful was in the 18s. It was related to majestic, solemn, and then over time it actually went to horrible, terrible, to a terrible meaning, right? And in the 90s, it came back to wonderful. I'm not sure. Maybe I'm getting too old, but for me, awful is still in the terrible and horrible part. In the middle part, we have broadcast, which was actually used initially for broadcasting seeds and in the field, right? And then it was much more related to newspapers and later on to television, radio, and so on. So again, this is over decades, but let me give you an example where things are very fast. Okay, so we did this analysis on a soccer match and what people were actually tweeting about the the soccer match. It was a soccer match between Internacional and Colo-Colo. It was one of the South American championships. And if you analyze how people were expressing themselves in terms of positive, neutral, or negative sentiments, you're going to see that it changes very fast. I mean, it's a matter of minutes. And this is totally related to events. So there's a foul or there's a penalty kick or whatever. So you can actually see as well what kind of words people are using to express themselves. We actually had to translate some of the words here to English, but you can see that in certain events, people were talking either about players or pressure or pushed away or things like that. And then later it changed to protests, penalties, and so on. There are some words that were actually redacted from here. I'll tell you that, but it's very interesting to have algorithms that are able to detect such changes on the fly. There's also another key example. This is regarding the Russia and Ukraine war. So here in this plot, we have the semantic distance between the word cotton and, for instance, operation, smoothly, rejoice, stubborn, brainless, and hohol. I'm not sure how to pronounce it, but actually the word cotton, over time, it became a synonym to brainless and hohol, especially, which are words that the Russian used to talk bad things about the Ukrainians. So again, this is in terms of weeks, but you can actually see how things are changing over time. So again, this is one of the things one of my PhD students is working on. He's going to be here in November, so in a few weeks he's showing up. And his big question is, well, how can we detect and actually adapt our models to such changes, right? He initially is focusing on BERT. Not sure if you guys are familiar with that, but it's an embedding for textual data, right? And he's actually testing many things. I mean, what happens if we fine tune it? What happens when we need to update this model? How can we sample the data in a decent manner to adjust the weights inside the embedding? And how can we add new tokens, new words to BERT? Because this is not trivial as well. So there are many experiments here, but he's actually proposing something which seems very good right here in the end. There's one key point that I'm going to talk to you about later on, but in regards on how you actually fine-tune these models, because we actually observed that if you train your model, I mean, your embedding with more epochs, the results actually become worse. Any idea of what's going on with that?
On which data set? I mean, like
it's textual data. We are using the Yelp data set.
One thing could be like it's kind of like in a way overfitted to that distribution,
yeah.
But in the concept sheet, you don't want to overfit to that distribution.
Yeah. What's going on here is that, well, if you train more to your recent data, you're actually forgetting what we had in the past. And this is what people in deep learning usually refer to as catastrophic forgetting, right? So when you start combining these things, you actually have issues from data stream learning, like concept drift, but you also have catastrophic forgetting, which is like very popular in batch settings, right?
But do you evaluate performance as you said before?
Yeah, using the frequential manner.
Does it make sense when you use multiple inputs?
Yeah, so what we are actually doing here is, well, I'm not sure if I have a flow chart of that. Yeah, I don't. So we actually start buffering data, right, until a certain limit. And we do have a detector. So whenever the detector tells us, well, we do have a change, right? We sample data from this buffer, and we actually go back to BERT and try to fine tune it, adding new tokens and also adjusting the weights. And this is like you actually stop the processing of the stream to make such updates, right? So we actually kind of interrupt that cycle, the sequential loop, right? During the training part. But we still respect that overall idea that we analyze one instance at a time, first for testing and then training.
It's just that when you evaluate on the data that you have seen already,
yeah,
you are overfitting also on your evaluation, right?
Yeah, that's the key point. So we're still thinking about ways to overcome this. We're not sure. But again, this is actually still better than the competitors. I'm going to show you that in a minute. We are also analyzing kappa because the data set's it's not really too imbalanced, but we just wanted to make sure we were not biased towards that. We do have some issues regarding runtime analysis as well. So if you look at the last part here at the bottom, runtime actually it's much worse than the others, right? Because we're adding so many things to the proposal, and it's hard to balance all things at the same time. And yeah, there you go. Here we have a comparison between what we are proposing against the hashing trick, which is a very trivial way of converting words into a vector, right? And we do have two other incremental approaches. We have the incremental word vectors, which was proposed by some colleagues in Chile. And word2vec, which is not really incremental, but we made some adjustments to it as well. So in terms of accuracy, looks very good. Kappa as well. And runtime analysis, this was actually very promising because we're not that bad in terms of runtime analysis when comparing to incremental word vectors and also word2vec. So not too bad. And again, already commented on this, but we see some characteristics of catastrophic forgetting here as well.
So I was wondering, right now, given the new embedded models, so BERT and Quantity a little bit small. So I was wondering, do you have any kind of experiment on the kind of like new language models? That how they?
Great question. That's the next step I'm planning him for. So one of the major things I want him to test is, well, as soon as he gets here, start working with large language models for sure. You read my mind. Okay, so I think my time's up. So I'm gonna leave you my email again, my webpage. So if you want to reach out, discuss any of the topics, just feel free to leave me a message, right? And of course, I'm gonna share with you somehow the slides, but I have many references here that should be relevant if you want to learn more about data streams. All right. Thanks again, guys.
Okay, yes. Thanks for the presentation. I just want to add a few questions. Like getting back to my earlier question. So you're assuming that in your scenario, you're getting streams of data and they're labeled.
Yeah.
Right. And you're able to use that to incrementally learn a model.
Yeah.
It can be done with ensembles or a single model. Okay. I get that, but so I mean, I guess the big assumption is that you'd be able to have labeled data.
Yeah.
On the fly.
Mhm.
Is that, are there situations, for example, if you took social media applications, is that something that's easy to obtain? Or?
Not really. Not really. Yeah, this is one of the main issues we have. Actually, I'm going to talk about two things here. The first one is, well, maybe you do have parts of your string that you have labels. Maybe there are some other parts that you have maybe some labels, and some parts you don't have any labels at all, right?
Right.
So there's a lot of research going on regarding semi-supervised learning, because if you have just a few labels, that's okay, you can use those labels, but in the other parts that you don't, I mean, you're just gonna waste that data, right? So this is actually a very hot research topic. There's still many things to explore here.
So some sort of online, but
Semi-supervised, yeah. It's very challenging, but I think that's a very good gap. I mean, there's plenty of stuff you could try, and not many people are actually familiar with data streams, but it's very nice. And just before you, there's my second comment regarding data sets in general. One of the biggest issues we have when working with data streams is the lack of data sets. And I'm going to tell you why. Because most of the data sets we are using these days, they are data streams, but we are not actually able to determine if they have concept words or not. Because one thing is having the instance labels, but the other thing is to pinpoint and tell, well, we do have a concept drift in this moment. This is not easy to tell.
I was thinking that self-supervised also could be very interesting, like self-supervised, like self-supervision.
Self-supervision. Yes.
Like, for instance, those language models can be trained.
Yeah, it makes sense.
Just to reproduce the next word.
Yeah.
And also, if you think about like a movie, for instance, can be a stream where you have audio and video, and this can be like a way to also have self-supervision. You try to reproduce audio, video, and so on.
Yeah, makes sense. Yeah. I think one of the key points here again is having the data to work with. Actually, again, labeled.
Well, in that case, you
do. Yeah.
And based on the requirement that you specified before for this kind of data streaming, I guess as soon as we go to the deep learning mode, we kind of violate 3 of them. So is it okay? Like, because it's not possible, at least right now, to not violate all those. Probably we just can keep one of those.
Yeah. If you go back to the traditional data stream literature, you're not going to hear about deep learning. And that's the reasons right here. As you told us, like, we have so many requirements that deep learning would just not be able to attend, right? But again, the ultimate decision on whether deep learning is going to be possible or not is the actual application, right? So if you think about, for instance, text data, it depends on how fast the data becomes available and how fast you need to process that. So it's tricky. It's really tricky. But again, there are some people trying to join these things.
Could you give me a real life example of where you need this application?
You mean streaming ones? I think credit card transactions is a very good example. So if you think about every time you swipe your credit card, I mean, there's a lot of steps on this process, right? And one of them is, for instance, anti-fraud systems. So if you go back to the amount of transactions Visa processes per second, I think it's roughly 30 grand per second. So you do have a lot of stream. I mean, you have a huge stream of data. And you could think about, well, I do have a static anti-fraud system, right? But I could also be updating the system on the fly. And I'll tell you why this is relevant, because if you have another fraudulent scheme, I mean, it's kind of an adversarial scenario, right? People are always trying to learn new ways of frauding the system, right? If your system is not adaptive, it's going to take a very long time before you actually realize something's going on. And then you actually have to learn a new system, deploy the new system. It could be days, it could be weeks. So maybe having a system like this would be beneficial.
But then you wouldn't have labels to know that.
Yeah, maybe you're gonna end up in something like this, right? In a semi-supervised fashion. Because I think you're gonna have labels for the frauds. Because let's say I have a problem with my credit card. I just found out that someone else is using it. The first thing I'm gonna do is call the bank, right? Something's wrong. This would be the label, right? You can also assume that the other instances, the other transactions would be like non-fraudulent.
And you can see that in a lot of applications, you're gonna get labeled by the application itself after some period of time.
Yeah.
Say if you're doing a recommendation system, or sending letters to someone with an offer or something, after a couple of days, you're gonna get, was it a good sent or not?
Or not.
So in a lot of tabular data mining, you get that after a period of time. So there may be a delay.
Yeah.
Or it could be a human in the loop that for this amount of data that you query, that you process, you could select
parts of it.
Part of that, the most informative to that, put for a human and feedback to it.
But then you wait to analyze this data until you get the labels.
No, it's already, you already predicted. So that's how we're gonna use it for improve your model data. You already predict the data because the data arrived like a credit card transaction. You're not gonna wait for that. You predicted it. But in order to fit to your model, may have a delay.
Yeah, you need to wait for the labels. Yeah.
For the labels.
But to update your model, you need
But for the prediction at the end, you receive or you predict. You receive, you predict.
But then you see 2 times the same label, the same data. Once to predict and once
to try.
Kind of you predict, you keep in your buffer, you can analyze it separately.
Another question. So you have an ensemble with models, and you have for each model a detector to know if you want to reset it or not. And you have actually 2 detectors for 2 levels, if I understood correctly.
Yeah, in the adaptive random forest, what we do is, well, we have 2 detectors for each member of the ensemble. Yes,
exactly. But you want one of them to trigger always before the other one, and you use different hyperparameters to tune that. Why can't you use the same one but with a different threshold, for example?
It depends on the detector.
Okay.
There are some detectors that work exactly as you mentioned. There are some that don't. So for instance, DDM and EDDM, they do have these 2 thresholds. So you don't actually need 2 detectors. But if you use Adwin or RDDM, there's no threshold option. Okay, so good question. It really depends on the algorithm itself.
You consider class imbalance to be a form of concept drift?
Yeah, as well. Yeah.
So what do you do? Because there are a lot of cases where maybe during operations you get, if you're detecting maybe failures, you get a lot of normal, and then all of a sudden you get a bit of normal. But that can differ quite a bit from the original training. And so what do you do in that case? How do you detect that?
Yeah, really depends on the algorithm. There are some approaches which are specific to this kind of problem. Yeah. So you can think about all sorts of issues here. You can think about features that are now relevant and then they become irrelevant as well, or vice versa. I mean, something's not really relevant and becomes relevant. So how can you adjust that? So class and balance, the same thing. What I like a lot about data streams is that you have so many challenges. So yeah, class and balance is totally relevant as well.
It could even be the case that we are talking about features, some features that exist in the past doesn't exist in the
Yeah. I do have a master student working on this as well.
Yeah.
And I like something that something I have in my mind that I think it's kind of like fitted into the, it could be fitted into teacher-student pattern, that you have some sort of oracle that's produced, for example, GPT-4, that you can just query really rarely to produce some labels and then use those in these frameworks. I was wondering, is it kind of something that is possible, kind of people doing in this framework?
Yeah, there is a paper called STUDD. It's an acronym for something, but it's exactly this idea: student-teacher approach for data streams. If you Google just STUDD, you're gonna find it. It's actually quite recent. I think it was from last year.
That's great. Thanks again.
Okay.
Just another, so we should normally have another, seminar in 2 weeks, but this one's gonna be a special one, mandatory, or highly, strongly recommended. It's gonna be about Olivia servers. And if that's not enough, we're gonna order pizza. So come and eat pizza. At least eat the pizza. But it's gonna be seriously very important, to learn about Olivia servers, and also know about good practices with the computing servers.
The pizza should be.
Thanks, guys.
Quiz at the end. You answer the quiz, if you get like 80%. Okay, you learn something.
Oh, we had also people online.
Oh, yeah.
Yeah.
I don't know if there are any questions.
Okay, guys. So for you that are online, do you have any questions?
Hi, Joe. It's Cassia speaking.
Hi
Can
there.
you hear me?
Yeah.
Okay. I have just specific question. I have been playing around with MOA and I was trying to understand Half-Deen tree. And maybe you can make it clear for me, because like is regarding the grace period and the Half-Deen bound. I was like, maybe I was making a confusion, I'm not sure. Because from what I understood, it was like, okay, the Half-Deen inequality, using the Half-Deen bound, I can, the algorithm will check how many instances enough to make a reliable splitting decision.
Yeah.
But is that correct?
Actually, the number of instances that will be checked is a hyperparameter.
Yeah, the grace period, right? That's why now I got confused, because
think about it on the opposite direction. So you have the user is going to set up the grace period, and this is going to be part of the formula for the Half-Deen inequality.
Yeah, so
and then you're going to use that information to be sure if you should split or not.
That's interesting, because now you have to have some intuitions about the grace period, right? That you have to set up.
Yeah, this is challenging as well. Yeah.
And the other thing is, at the end of your presentation, you were putting their accuracy, and I was like, accuracy was like 46. This is percentage of the results.
Yeah, percentages.
Yeah, that's so low, right?
Yeah, I actually didn't give you enough details about the data set. In practice, this is a 5-class problem. So it's not really low. It's not too bad. Maybe I should have gave you more details about it.
But that's okay. It's got me like, okay, that's.
Yeah. No, it's a 5-class problem. It's somewhat imbalanced. So 40% is not too bad. Okay.
I have a simple question for you, Jean-Paul.
Sure.
Did you invest, for example, about the sampling process related to the, for example, if you have a data stream with high velocity, you know?
Yeah.
So maybe it's not necessary to ask the operator to label or to provide the true label considering all the samples. So it means that if you are using some metric related to the hard to classify.
Yeah, confidence maybe.
Yeah, something like that.
Yeah.
You know? So maybe it could help in order to learn. I mean, sample located close to the boundary.
The boundary, yes, perfect. Yeah.
Did you investigate some approaches related to this class of algorithm?
There are some papers on it already. I believe the one that I talked to you about before, which is called the student-teacher approach, it actually uses something like that. So it actually tries to identify if the instance is close to the decision boundary. If it is, then you ask for the oracle for a label. But this is also used in some class imbalanced situations as well. So there are a couple of approaches like this already.
For example, this class of algorithm can help in order to detect outliers.
Yeah, as well.
And avoid, I mean, considering these outliers in order to update the model.
Yeah.
Something like that.
Yeah.
We can discuss these topics tomorrow.
Sure.
Thank you very much for the seminar, by the way. It was very interesting.
Oh, you're welcome. Thank you, guys. Anyone else? Sure. Okay.
Thanks.
So yeah, I'm gonna finalize the session. Thanks again, guys.
Thank you.